Alright, it's time to start using all the formulas that we have derived. So I'm going to start by solving a few examples, and a priori let me tell you that all the examples are going to be solved problems from Klepner. Now you must be wondering what's the need to solve them all over again, but these problems are so important that I would like to just go through them once, and though what I would suggest for you is just try to solve it, read it on your own, and then only then, if necessary, watch this video. So this is example 6.14 and it's on page number 262, and this is Kepner and Kolenko edition 1. Okay, so let's start. What does this example say? Or maybe we should just quickly make the list of formulae that we have derived for we are in particular looking at the application of the key formulae, which is force external is equal to mass into acceleration of the center of mass for the rigid body. We're talking about the rigid body, and we are talking about translation plus rotation, and you can already see that the translation is taken care by this equation and the rotation is taken care by an equally simple looking equation, which is tau cm. We're talking about a particular problem where the axis is always parallel to the z axis, and this is equal to ICM alpha, and we emphasize that this is due to the special properties of the center of mass of the rigid body. And all of this one comes from the law, another law, which says torque external on the system is equal to change of angular momentum of the system with respect to time. So this is the law, and from the law we derive this equation. So let's start, but along with this, especially when we focused on this law, we derived two more formulae, and it's better to get acquainted with those formulae as well. So what are those formulas? Torque on at any instant of time, frozen instant of time, is equal to RCM cross the total force external on the system plus tau cm, the torque about the center of mass of the forces at that instant. So the other one is more interesting, equally interesting or more interesting, that is the angular momentum of the rigid body. Okay, the angular momentum of the rigid body at that instant of time. Let's focus on LZ. This is equal to RCM cross MVCM at that instant, the velocity of the center of mass, plus ICM into omega t at that instant of time, and omega t is the omega which is as observed from a observer who is traveling along with the center of mass. Okay, traveling along with the center of mass. So for him, the body only can do pure rotation about center of mass, and we have discussed this in detail now. So let's get on with problems which use these formulae. And the first problem is definitely very well put by the author. He talks about a road and a disk of mass m and maybe radius r, small r, which is rolling on the road, and the question is, what is the angular momentum of this object? So let's get the notation in place. This is the x-axis This is the y-axis, this is the z-axis. There is little doubt about what the origin is, and this disk is of mass m and rolling without slipping. So this is the first time maybe that we are talking about this constraint, and it's going to be very important, and so we will spend some time on this part of the information, that the disk is rolling without slipping. So what does that mean, and how does it enter into the way we are going to solve this problem? And it is given that this particular object is the velocity of the center of mass is known. Okay, the velocity of the center of mass is known. Let me have another quick look at the problem. One second. I'm a little surprised. Okay, right. He has said that the angular momentum of the particle and is known. So I'm sorry, he is saying that omega is known. Okay, I'm sorry, omega is known. So in terms of omega, he wants the angular momentum of this disk which is rolling without slipping. Okay, so we just go and apply the formula, and well, what is the formula? Let me just write it down. Lz is equal to R Cm cross M VCM plus so this is not what I wanted to write. I wanted to write that omega is known, and plus ICM omega. So what you can see now is that omega is known, and ICM, you can look it up from the tables, is mr square by 2, where m is the mass and this r is this radius. So no problem here. So we're done with this part of the formula, or actually we haven't done. Okay, so now I'll tell you why I'm saying that we are not done with this. We've got to give it a sign. Please note that while Lz is along the z-axis, it could be out of the plane of the paper or into the plane of the paper, meaning that it could be in the direction of plus k or minus k. Okay, so what I'm trying to tell you is that we got to give it a sign. Now if you notice, if you think of yourself as the observer, this is the center of mass, there's little doubt about that. If you think about yourself as an observer who's traveling along with the center of mass here, then you observe that the wheel is rotating clockwise, and that would mean negative. Okay, so I've got this part right. I'm happy about this. Okay, into omega, and the problem says that omega is known, so everything seems to be fine. So but this minus sign is important because I'm now adhering to the sign convention, which is anti-clockwise is positive. Right, so now we'll worry about this term in a slow fashion. I'm going to draw it again on the next page, but just would like to tell you that what is obvious is that V center of mass is in this direction, okay, whatever it is. And the other obvious thing is, what is the position vector RCM? You got to start from the origin and go all the way till here. Okay, so I'm going to redraw this. So whatever I need, RCM and VCM is staring at me. Mind you, VCM has not been given, omega is given, and VCM will be related to omega by this constraint, which is the other part of the things that we want to learn in this particular lesson. Right, so let me get back to repeating this. So there is a fixed coordinate system, and this fixed coordinate system has an origin, which is pretty much making the question meaningful, because I've been emphasizing that for asking this question, what is the angular momentum of the system or of this rigid body, you got to tell me what is the coordinate system, and in particular where is the origin. So this time maybe I'll draw a better circle, and now let's get going with the other term, which is this is RCM, and this is VCM. Now what is the first term for LZ? It is equal to RCM cross VCM MVCM plus something that we've already done, so let's not discuss this again, MR square by 2 into omega. And this minus basically means it's into the plane of the paper, minus K. Okay, now look here. What is clear is that this is the theta, is the angle between R and VCM, and the magnitude of this cross product I can tell you quite easily. But more importantly, if you could just imagine a little bit and use your right hand rule, you'll quickly agree with me that the cross product of RCM cross VCM is into the plane of the paper. That means it's got a minus sign. So I'm going to leave it to you. Please play with your right hand and rule, and let your thumb point into the plane of the paper. Now let's look at the magnitude. Magnitude is RCM RCM sine theta into MVCM plus something that we already know. And now this is very nice, because I think you'll readily agree that R sine theta is this blue thing. This is nothing but R, which is nothing but RCM sine theta. Okay, so this can be replaced by R M VCM minus half mr square by 2 omega. And we've gotten a fair distance now. So please pause this video if you have some problem, but let us now proceed and make a further simplification to this. So the answer is LZ is equal to minus R M VCM, which is not been given in the problem, minus R square by 2. Well, we know what small r is. It's the radius of the disk, into omega. Right, now there is a constraint which we still haven't used. The drum is the disk is rolling without slipping. So we're going to now discuss this, and let me tell you a priori what is the result. This constraint is going to give us a condition that VCM is going to be equal to the magnitude of VCM is going to be equal to the magnitude of R omega, and therefore what we're going to end up with is that this is equal to minus R square M omega, and then again minus m r square by 2 omega, and then this is going to be equal to minus 3 by 2 m r square omega. So all that remains is to convince you of this, okay, and then we are done, and you will accept that the answer to the problem is that the angular momentum of this drum with respect to the origin as given in the problem is in the negative k direction, and its magnitude is equal to 3 by 2 m r square omega. Right. So let me now proceed with the last part of the problem, which is to convince you that the what is the constraint for rolling without slipping, and how does one go about it. It's very simple. Might only be the only novelty is here is that you're doing it for the first time. So let's see. The way to do it is that what do you mean exactly by rolling without slipping? So at a frozen instant of time, so at some instant of time which you froze while this whole phenomenon is happening, try to focus on the point of contact. So the point of contact on this particular wheel and the point of contact with the floor. Now the yellow dot does not slip on the white dot. So that is the meaning of rolling without slipping. The yellow dot does not slip with respect to the white dot, which means that the velocity of the yellow dot at that instant, is equal to the velocity of the white dot at that instant. Now this clearly is 0 because the white dot is on the floor and the floor is stationary. So for this observer is going to claim at that frozen instant of time that the velocity of the yellow dot and the white dot is equal, and that means no slip. And if that is true, then we say there is no slip. So let's see what is the velocity of the yellow dot at that instant. Okay, now this has to be done in 2 steps, which is what is the velocity of this observer who is traveling along with the center of mass. It's like you can imagine that this observer is moving with a velocity in this direction, which we are calling the velocity of the center of mass. So it's like he's sitting on a car which is moving forward with the velocity vcm, and you ask this observer what is he seeing of the disk. The disk is moving to the disk is going in uniform the disk is moving in pure circular motion, and according to this observer the velocity of the yellow dot is in this direction, okay, and equal to r omega at that instant. I'm sorry, we've been using the small r, okay, because this is in my problem this is small r. So r omega in that particular direction, okay. And what is the, if that is the case, what is the velocity with respect to the eyes of this observer? So he will say that the velocity of the yellow dot is equal to minus r omega, okay, plus the velocity of the car, which we are calling it as vcm, and this, as per the eyes of this observer, is equal to, I'm actually going too much of an overkill, it is equal to the velocity of the white dot, okay, as per the eyes of this observer, because he's saying aloud that there is no slip, and what he means is that this is equal to the velocity of the white dot, which happens to be 0, and this implies what I claimed initially, that the magnitude of the velocity of the center of mass is equal to the magnitude of r, which is the radius of the disk, into omega at that instant of time. Okay, so this is the so-called constraint equation for the rolling without slipping. I think I've been rather hasty here and not followed the sign convention very well. So let me try one more time with the sign convention. So anyway, this I want you to understand, and the problem per se is over. But let's say that we happen to know the omega. So the omega, as per our sign convention, is actually minus of omega, because omega radians per second has been specified in the problem, and as per our sign convention it's minus, and therefore the velocity of the yellow point due to pure rotation is going to be minus r omega. Okay, and then then I think we're okay, and VCM is positive, and minus r omega is equal to 0, and that implies that VCM is equal to r omega as given in the problem. So maybe we'll have occasion to follow the sign convention in other problems. So I don't think I've done very well in this problem, but I think I'll just let go and let you ask me something if it's not clear. Meanwhile, I would like to proceed to the next problem. Thanks.